For the first part of our notes on molecular geometry, we're going to look at the different types of covalent bonds that you can form. We mentioned before that you could have a single bond, a double bond, or a triple bond, but let's look at what exactly those bonds are made up of. If you look back here, and think about a covalent bond in general. Covalent bonds in general are bonds that are formed between two nonmetals. And if you look at the periodic table, you'll see that those nonmetals are in the P block of the periodic table. Now, what does that mean, the P block of the periodic table? It means that all of the valence electrons in those atoms are in P sublevels. So those are the electrons that are going to be involved in bonding. So also remember that a P sublevel looks kind of like a figure 8 on a two-dimensional surface. The best way is to imagine two balloons tied together to get it to a 3D image. And also remember that a P sublevel has 3 orbitals. So those orbitals have to be oriented around a central point. And this example right here is one of the best examples I could find. I've always used balloons for it, but we can't have balloons in the school right now because we have people with allergies. And I can't really do balloons on the videos like this anyway. So this example just shows what would happen if I took 3 different P orbitals and oriented them around a central element. If we had that central, or not the central atom, if we had the nucleus here, then we would have 1 p orbital on the x-axis. We can call this the y-axis. It's kind of off-center a little bit, but there's the y-axis, and then we can think of this as the z-axis going back into the board. I really didn't do a very good job of showing those attached to the central element, but my point being is that we would have all 3 of those orbitals around that central point, and that would represent a set of P orbitals, a P sublevel. So let's imagine 2 fluorine atoms. Those 2 fluorine atoms are each going to have a set of P orbitals around them. Specifically, the valence electrons are going to be in the 2p sublevel. Let's look at why. If you look at fluorine's electron configuration, or orbital notation would be even better one to look at. We've got 1s, 2s, and then 2p. So in the 2p, there are 5 electrons, which leaves us an orbital that only has 1 electron in it. So 5 valence electrons for each of these fluorines. So let's imagine that that single electron is in this px orbital, the one that's on the x-axis. So as these 2 fluorine atoms approach each other, the very first orbitals that are going to come in contact are going to come in contact just physically. Imagine these being balloons. They're going to come in contact head to head. So when they do, those electrons, we start that bonding process, and the electrons start being shared. And they're shared between those 2 fluorine atoms, forming this head-to-head type of bond position, and this is called a sigma bond, and a sigma looks kind of like an O with like a little tail at the top. So that's a sigma bond. Every single pair of elements that bonds first with 1 sigma bond. Now there are other types of sigma bonds we're not going to get into. I wanted to show you these ones that are happening with these non-metals today. So let's take now 2 oxygen atoms. Now oxygens are 1s with 2 electrons, 2s with 2 electrons, and 2p with 4 electrons. So in this case, we're going to have 2 orbitals that only have 1 electron in each. So let's imagine our 2 original ones here with only 1 electron in each. Kind of look like eyeballs. I imagine like little turtles staring at each other. But anyway, we've got those 2 electrons that are meeting up in orbitals head to head. Now let's say we've got the other pair of electrons, our other electron in these orbitals up here. keep in mind that this orbital extends from here to here, and on this one from here to here. So when the first ones meet up in the sigma bond, this head-to-head bond right here, we're going to get that sigma bond again. But these other ones, after that sigma bond forms, these can't meet up head-to-head. They're not in the right geometry to meet up head-to-head. If we force this to come closer, which it would have to do in order to form this next bond, because oxygen is going to do a double bond. We've seen this before. When it forms the second bond, it's not going to be a head-to-head bond. It's not going to be another sigma bond. It's going to be a side-to-side bond. And this is what happens. We get this blending. So we're going to get a blending across the top, and we're going to get this blending across the bottom. And a pi bond is going to look different than a sigma bond. A pi bond is going to have that blended area across the top and the bottom. Together, that's one pi bond. And then, of course, in the center here, we have the sigma bond. It's not a very good sigma. So there's a double bond. So a double bond consists of one sigma and one pi bond. One sigma, one pi. Up here, we have, in the fluorine atoms, remember, one sigma only in a sigma bond. But let's go a little further. Let's say this time we've got nitrogen, and we've seen nitrogen structure before. Nitrogen structure has it forming a triple bond. And so we're going to get more than just that single sigma, or even the double adding on a pi. Let's look what happens here. We've got electrons here, and I'm going to draw this to show you what happens. For hydrogen, we get this. It has 3 electrons in that 2p sublevel, so we're going to have 3 orbitals that only have 1 electron in them. So I'm going to draw all kinds of little eyes here, representing the orbitals that are going to hook up. So again, keep in mind, we'll get this sigma bond forming first. That's always going to happen first. So there's a sigma. And now we're going to be blending side to side. That sigma was head to head. That blue sigma bond is head to head. Now we're going to be blending these two side to side orbitals into a pi bond. And look what else has to happen. In order to form that third bond, we also need to match up. I'm going to draw this one in green instead of blue. Maybe it'll show up a little bit better. We're going to do this one. Here's that p orbital, and here's the other p orbital here. And look how they're going to match up as they get close to each other. Is it going to be a head-to-head bond this time? No, it's going to be another side-to-side bond. So we're going to form this other area here and here, blending those two orbitals into another pi bond. So if we've got a triple bond, we're going to have a sigma bond, that blue sigma. We're going to have this red pi bond. And I'm not going to draw another pi there because that would make it look like we had 2 pi bonds. Remember, a pi bond has an area above and below the nucleus, above and below that structure. And we have another pi bond forming those electron cloud areas above and below as well. So that's your triple bond. A triple bond has the single sigma bond and 2 pi bonds. So what do I expect you to be able to tell me out of this? I expect you to be able to look at a structure like this and to analyze that structure and tell me how many sigma bonds and how many pi bonds that structure would have. So looking at this, I'm going to mark all of the sigma bonds with blue. So there's 1, 2, 3, 4, 5, 6, 7, 8. And I have a lot of people that tell me there are 8 sigma bonds, but they've forgotten that every single bond between any 2 elements is always going to consist of a sigma bond first. So all of these double bonds also have a sigma bond as one of those bonds. So we have 8, 9, 10, 11 sigma bonds. And remember that double bond has also a pi bond in it. So each of those double bonds has a pi bond. So we end up with 3 pi bonds. So 11 sigma bonds and 3 pi bonds. And if there had been a triple bond in there somewhere, then we would have ended up, again, with a triple bond having 1 sigma and 2 pi bonds. So make sure you can add all of those up. Now, what kind of characteristics do these bonds have? First of all, a sigma bond is stronger than a pi bond. Okay? And it's all about the physicality of it. It's all about the geometry. In order to form the sigma bond, it's really easy. They meet up, and you can see it up here. They meet up head to head. It's really easy to get to. Physically, they just get to a sigma bond easily. When we start forming pi bonds have to stretch across to meet up. And if you try to do it with balloons, you can see it really physically that happens. And so it's easy to snap a pi bond. So a single sigma bond is stronger than a single pi bond. Pi bonds are easy to snap. But when you look at all of the bonds together, a single bond is going to have a sigma. A double bond and a triple bond are also going to have a sigma. But a double bond is going to have a pi, and a triple bond is going to have 2 pi's. When you put those bonds together, that's going to overall make a single bond the weaker or weakest of the bonds, and the triple bond the strongest of the bonds, simply because there are more bonds there. It's like being in a fight, one strong person fighting one strong person and 2 weaker people. I'd still say the 3 are going to be better off. So triple bond stronger. Triple bond is also shorter. Keep in mind the physicality of it. As those pi bonds are formed, you keep having the nuclei of the 2 atoms being forced closer and closer together so that you can stretch those p orbitals across and get them to match up side to side. So the single bond is the longest of the bonds, and the triple bond is the shortest of the bonds. So when you talk about bond association energy increases with bond order. What the heck does that mean? Well, bond order is easy. A single bond simply has a bond order of 1. A double bond has a bond order of 2. A triple bond has a bond order of 3. So if you have a bond order of 3, you have a triple bond. It's the strongest of the bonds. So it's going to be the strongest, the hardest to break. So it's going to require the most energy to break that triple bond. So, and the least amount of energy to break that single bond.